Okay, so Unit 3 is physical and chemical properties of materials. I forget this little pointer thing. Let's go. Alright, so thermal properties. So when you think about thermal properties, I think you might probably think about temperature, okay, and fire. So that's usually think in thermal properties. So these properties they're just the responses. Okay, since we're studying materials, we're gonna take a look at the material, how they respond to the change in temperature. So temperature is when you go all the way down to the structural level. We're talking about how these atoms, okay, they move. Okay, they always move. So when they move, and these activities at the molecular level, atomic level, and you measure the activity by using a particular instrument, and we call them thermometer. Okay, there are many different kinds of thermometer to study. And when you study these little things moving around, you see, okay, the little tiny liquid that we put in the thermometer instrument, they rise up, okay, showing like they're actually moving at the atomic level. And when you stick that thermometer into a material, let's say a liquid, wanna take the temperature of that liquid. So if you take chemistry 1, 2, or physics, then you're gonna get a hold of a thermometer instrument, different kinds of instruments. And some of them are very old and long, okay? Thermometer, all you have to just stick that, okay, little mercury tip into the liquid, and you're gonna see start to rise up, okay? But at the molecular level, what is going on? Okay, atomic level going all the way down. So these guys are moving. It's just the temperature is an indication of, okay, on how much they're moving. And we call that temperature. Change in temperature, in order for them to move, we have to use some sort of energy. Can usually come from heating or using fire, things like that to change, okay, the temperature of something. So that's why when you vision the thermal properties, you're always thinking about heating something, okay, fire, and the temperature go up and down. So when you think about change the temperature, you are using energy of some sort to make these internal structure move, okay? So thermal properties that need to be considered when selecting a material. So we're going to look at all of that, okay? In your product design, you have to select the material. Every time we select the material, we're going to take a look at the heat resistance. So now we're coming back to our level, not at the molecular level, but our level. So at human level, this is what you usually see and feel, okay? Convection. So you can put your hand right here and you can feel that heat, okay, coming off from here. But in real thing behind all of that, what we see is this energy source, okay, is literally inducing kinetic energy, okay, into these molecules in between your hand and here, and they start to move and come and, okay, bump to your hand, and your hands start to feel because you have sensor inside of your body systems, and these sensors are they can be able to understand the movement, okay, of these tiny little structures. So we go down to atomic level, electrons, neutrons, and protons. Okay, these guys move. You don't need a lot of energy for them to move. They could move like hell and come, and they can also move the materials that made of you, that make up of you. So that's what you're feeling, okay, heat. And we call that heat. It doesn't exist what exists physically is these guys moving, okay? The medium moving and your cells moving. Your cells is composed of too many atoms, okay? And these guys moving all the way down to the internal structures. Your electrons, and then your protons, and then your neutrons, okay? Because we're not going to go all the way to quantum level. There's another level down there, okay? They all move. And every time they move, they change the structures. Every time they change the structure, you feel all of that, okay? So, a pretty interesting phenomenon that we're living in this world. But then, when we feel at our level, okay, our system level, then this is what we usually see and feel. Radiation, and then we have conduction going through a medium. Here in this case, the ion, okay, pole. Alright, so we'll take a look at the heat resistance, thermal conductivity. So this is, we're looking at all these properties at our level, okay? Heat, capacity, thermal expansion, and then thermoelectric behavior. So when you think about the thermal conductivity, for selected material for a product, we're always thinking about the insulators, okay? Because the metals can conduct, and some of them you don't want this conductivity to happen, so you have to come with a means to stop, okay, or protect. So that's we develop insulators. Okay, like your house is insulated completely. If your house is not insulated, okay, it's not going to be good, because you're going to feel intense heat and cold. So heat capacity, thermal expansion is a huge thing for construction industry. Because if you didn't calculate in the right way, then you will have incredible amount of issue in your building. Okay, precision instrument we use, okay, a lot of thermal expansion calculations because you need the instruments to measure correctly. Thermoelectric behavior. So we're going to take a look at the thermocouple, okay, applications, things that we already know. Okay. When you think about the heat resistance materials, some of the materials, they have ability to maintain their desired, okay, mechanical strength. Even at the elevated temperature, meaning very, very high temperature, okay, they can maintain their mechanical strength. Meaning that they can maintain their structure, and mechanical strength comes from their structure. So even though you're like heating it up all the way to very, very high temperature, they're going to maintain their mechanical strength. So things like ceramics and metals and polymers, okay, ceramics can stand all the way to 5,000 degree Fahrenheit. Okay, this is a common temperature in the lab. We usually use the degree Celsius or Kelvin, okay, because they're smaller, so it's easier to handle in calculation. Metals maximum is 1500 degree Fahrenheit. Polymers, they can stand all the way to maximum 500 degree Fahrenheit without losing their mechanical structural strength. So if you heat it up over that, okay, they're going to D-shape, yeah, and be destroyed. You would be going into the destructive zone. So these are the maximum temperature they can be able to stand. So transition temperature is just a point, okay, so where below that point, the material, they're going to lose its ductility, okay? So ceramic is above 1000 degree Fahrenheit. Metals is between 200 degree Fahrenheit. Okay, that's already minus 200 degree Fahrenheit and 200 degree Fahrenheit. Between, because there are many different types of metals, so it depends on, this is just a range, okay, giving you a temperature range that include all different types of metals, okay. But whatever that is below that point, okay, they're gonna lose ductility. Then polymers, the same thing with metals, okay, between minus 200 degree Fahrenheit and 200 degree Fahrenheit. So this is ceramic material, that's metal, and then those are your plastic, your polymers. So if you forget about what ductility is you can review your physics, okay? Just like the material, they just want to maintain their shape, okay? and they have ability to sustain a very horrible deformation, okay, under some sort of a force, or so meaning like they can prevent themselves from deformation, okay, so that ability they have it. But after, okay, this is like above 100 degrees Fahrenheit, that's between this and this, between this and this, okay, these are just a point that we're giving to these materials, ceramics, metals, and then polymers, and they have their own point. Okay, below that, they cannot be able to prevent themselves from deformity. Okay. Okay, then the next step is you're gonna be start thinking about, okay, what's the mechanical strength and what's the ductility? Well, this is kind of like something that you draw and the material can stand it. Okay. Uh, but below this point, you can't be able to stand that kind of, okay, you cannot be able to do that kind of drawing in these material. It's just like draw. Um, this one is a structural mechanical strength. Okay, they don't lose a structure up to that temperature, but they lose their ability to stretch a little bit. Okay, like elastic, but not entirely lost it, and lost the ductility. That kind of ability, you lose it up to that point. Yeah, but they can maintain the mechanical strength up to this temperature. Yeah, ductility and mechanical strength is totally different thing. Yeah, this is kind of, I would call it like, I usually take this like a lost day, and you can draw the material to a certain point. Okay. So in material, here is your transition temperature, and okay, above that transition temperature, okay, material, they are ductile. Okay, you can draw them, and below that they're brittle. Okay, yeah, they become hard. So that's brittle, and then this is kind of tough, so that you can draw. You don't have to worry about all of the lines. Okay, we have to just like, here is a temperature transition. If you go below brittle, and if you go buff, you've got ductile. Okay, and you still have your ductility. This is just showing you the energy lines. Okay, for different metals. Here is a BCC line for metals, ceramics, and polymers, and this one is a high strength materials. Okay, don't forget your body center and face center Q. Yeah, that BCC and FCC from your previous chapter. Okay, conductivity, thermal, and then conductivity. So another ability of material, and the conduct. I already show you the picture. You can transfer heat from a body, okay, of higher temperature to a body of lower temperature. So that ability is entirely, okay, determined by, again, internal structure. Okay, internal structure. So the higher the thermal conductivity of the material, you're gonna have the faster the heat, okay, can be conducted through it. If you have a higher conductivity, the heat is gonna transfer through it, okay, pretty fast. Alloys, your impurities, they're not good because they're going to decrease that ability, conductivity. Okay, so you know, pure metals are favored. Okay, if you want to design your product to do conductivity. Okay, and definitely you don't want impurities, dirt, the structure dirt. All right, so this one is just a table, and here we're seeing thermal conductivity. This is not a physics class, so you don't need to stress on the unit, but you should know, okay, what that is. So here is the entire package of your unit. So thermal conductivity, we go with a little k. So that K is the same as your watts, right? This is per meter, so it has a -1, and then per Kelvin. And this one we call the thermic coefficient K. Okay, just the coefficient is a mathematical part, mathematical adjustment formula. So we have metals, your polymers, and then your ceramics. And we're taking conductivity for these materials, okay, different materials. And they're like, so pay attention to how it goes down from silver to the stainless steel, okay? So what are you looking at? Conductivity, pretty good, yeah? Silver, good, good. And then go down. They don't conduct too much, stainless steel. Polymer, the same thing, yeah? This is higher and that's low. Thermoset, and then your wood, nylon, and then your thermoplastic, okay? Going down. Ceramics, silicon carbide, okay? And go down all the way to glass. It's not conductive, yeah? Huge number. Very, very good. Thermal conductivity. Tiny little number. They're not conducting, yeah? Then we're going to review heat capacity. So heat capacity is just efficiency. Material efficient, okay, in many different ways. So this is one of them. So that efficiency is they can absorb the energy, okay? They can absorb this type of energy, meaning like when something is moving, that pump can move uh, some of the material, okay? So heat capacity is heat. Again, heat is the transfer of energy. What kind of energy? Most of them, we have a basic two major energy, kinetic and potential, okay? Usually kinetic is being transferred. And the little tiny things moving around, and we measure, we call that temperature. And usually these little tiny things, they move around because they are being energized, okay, by a source. So heat capacity is just the amount of heat, okay, needed to raise the material 1 degree. Because of the way we write, students, they usually get misconception. And that is like they're like going back to our level, so our system level, and always think heat is a physical thing. And we always describe heat as something hot, yeah? Something red or hot, or something that you can go and feel with your hand and you feel hot. Well, that's true, but only at our level. But you've got to know the internal, all right, internal level, which is all the way down to your atomic structure. So at atomic structure, heat is completely described as a movement, okay, movement of these little guys. And we have such a modern technology is so powerful because we have discovered that movement and can be able to derive them systematically, okay? They move naturally by themselves, but now we are driving it systematically. So we can control these little guys now. So we have more and more sophisticated and powerful technology today. So it's the number of, again, with the measurement calories you measure, okay, that amount. So this amount of calories needed to raise 1 gram material, and we're going to raise 1 degree Celsius or Kelvin. So here for water, heat capacity, just 1, you need 1 calorie, okay, to raise 1 gram, okay, of material to 1 Kelvin. Thermoplastic polyethylene, you need 0.54 calorie, okay, to raise 1 gram of that material, okay, to 1 Kelvin. You have glass, you need 0.14 calorie, okay, to raise 1 gram of that glass, okay, and we want to raise 1 Kelvin, okay, that's just a measurement temperature. Iron, you need 0.11 calorie, need only a little bit, because iron is pretty pure metal, okay? To raise 1 gram of material, 1 Kelvin. So that's we call it the efficiency of these materials to absorb the thermal energy. Expansion. So material they expand when they're heated. Okay, that's mean like energy transfer to them. Why? So you gotta go back down, not at your system level. We're gonna go all the way down to atomic level. They expand because they're moving. Every time they move, they're taking space. Every time they take space, okay, it's kind of a space holder. So every time they take space, you can see the expansion from our level when there are too many of them. Yeah. So when you're seeing like a bar of iron, that's a lot of gazillion of atoms right in there. Yeah. So when you heat it, they're gonna absorb that and then they're gonna expand, meaning like they're gonna go crazy inside and move around and take space. And from our system level, we're seeing human system, okay? We're seeing that as an expansion. Mess around, yeah, your construction. And when you cool it down, they're gonna contract, yeah, back, meaning like they go back to the potential energy from kinetic energy at the atomic structural level. So here is our mathematical expression showing that. So you don't have to remember any of it. Since they expand, we're looking at the length. Okay, that's little delta is showing you how much it expanded, and then that's your original length. Original length, that's the expanded length. Okay, above this much above that. Okay, is equal to. So if you want the entire expanded length, you're gonna add this and that. Yeah. So that's your original length, and then plus delta L is going to give you the expanded material. So here we're looking at how much, okay, it got expanded over the original length. So that much expanded. And you have an offer right there. And your offer is not just a coefficient, okay, adjustment, linear thermal expansion, the times, okay, were expanded because of that amount of heat. So therefore the change in temperature. So it was a normal temperature, room temperature, we heat it, we have a higher temperature. So you minus, okay, the normal temperature from the higher temperature, you're going to get a delta T, okay? Delta meaning like the change in the temperature times the coefficient of your linear thermal expansion depends on the type of material, and you're going to get the change in length over that original, okay, length, okay? So every time you take a look at the equation, you don't have to remember anything. You just truly need to understand what's going on and can be able to write that with some symbols, okay? Because writing like this is compact than writing like that. You know, nearly all material expand when heated and contract. When cooled is bulky. Okay, it's not very precise. This is pretty precise. Tell you exactly, okay, how much been heated, how much been expanded, how much we've got before, okay, and what kind of coefficient that is multiplying according to this, okay, change in temperature, yeah. So we have a fraction here. So you go back to your algebra mathematic review. So this way to offer is inversely proportional to original length, and offer is directly proportional to original length. So as this delta T. Okay. So the more you change or increase the temperature, the more it's going to expand it. Yeah. Okay, so coefficient of linear thermal expansion, another table showing you material. And then here is coefficient of thermal expansion. And we're looking at the room temperature, okay? And we're studying this little offer right there, okay? So that's offer Ln 10 to the power minus 5, and then Kelvin, so that's per Kelvin, okay? Minus 1. Kelvin to the power minus 1 is just per Kelvin. So these are, like, if you write it in a fraction, they're going to go down under this, okay? But you don't have to go into details again. Not necessary. Nobody's going to ask you back mathematics or physics. Here is you're concentrating this material. So we have the hard rubber and aluminum go all the way down to glass. Yeah. And here you can see pretty much going down, except this copper and brass, I think this is supposed to be up and copper is supposed to be down, okay? Because copper is only 1.67 and brass is like 1.8, okay? Um, so you can be able to see the trend. So the material, hot rubber, they've got bigger coefficient, which is this guy. So what they're gonna expand, okay? They're gonna expand a longer, yeah, longer length. Aluminum expand good, and then go all the way down. They don't expand too much in glass, yeah. Alloy not so good, but alloy is not, they're kind of like not pure, yeah. So not pure material like rubber, aluminum, or brass, or copper, iron. So their coefficient go down, yeah. Again, we're going to stick to linear expansion. We have many different kinds of shape. Don't forget that. This is just like a real simple, okay, one. We have many different kinds of shape like this or that. So that's going into your derivative and integration. So go into your calculus. Right now, I just stick to regular linear thermal expansion. Very basic one of them. Okay. So here we have thermal expansion, very important in designing, because if you make a mistake in calculation, you're gonna get all wrong design and they're gonna mess up every time the temperature change. Okay, so you have to include the temperature change and thermal expansion of your material in your design and give them some space. Yeah, because they can again cause stress in the immediate components, and all your materials components, they're not just standing alone, they're always standing with something else in your product, okay? Because you're always attaching or attaching permanently, attaching temporarily, because you have to attach one part to another part. Okay, there are many different ways that we use to attach. Use fire or use glue or use a different kind of attachment or technique. So here it's just showing you if you have a larger thermal expansion, okay, it's going to cause a stress in the next component. So we have two different material right there. One is steel and the other one is ceramic, and they have different, okay, they have different thermal expansion ability. Is different. So let's take a look at it. What happened? So this is what happened. Yeah. So metal one and the metal two, alpha ones. Okay. Here, this is your legend is showing you this metal has alpha one, which is your coefficient linear expansion, is greater than alpha two, so that was going to expand more. Yeah. So it did. Yeah. It go down. So it hit the second metal right there. Yeah. And causes stress on it. So it bends. Yeah. The whole thing bends. So what you have to do is you've got to come up with a design that is going to prevent that expansion. Okay, so we need to put more stress right here, and we also need to give some space for that to come down. Okay, in between this and that. So these are all the design. But again, you don't have to design. You only have to know the process of it. And if you do go into industrial material line, you might have to also get mechanical, okay, engineering subjects along with it, and also the product design with it, and you can make a lot of money in that line as well if you want to follow money, okay, as an option for you. The next one is thermoelectric. And we're going to study two effects. One is your Peltier and the other one is your Thomson, okay? But it's the same thing anyway, the design is a little bit different. So the first one is your Peltier effect is just a behavior again, okay, when we deal with the thermoelectric stuff. So what it does is it's going to create something called voltage. You already know what voltage is, okay? So voltage is just another difference, okay? And we're looking at the potential, electric potential difference, but they're different from one point to another. Just like your temperature difference, okay? That's what we're looking at for voltage, okay? Voltage difference. So we got a voltage difference across the junction, all right, when two different metals, again here material is particularly metals, when they're brought together. So you're going to bring one metal and you're going to bring a second metal, and then you're going to bring and put them together. Okay, and every time you put two things together, you always have a junction. Yeah, so we've got the voltage across the junction when you put the two metals together. Yeah, so here it's just showing you right there, metal 1 and then metal 2. Yeah, and you have a hot junction, and this is just a cold junction, this is a hot junction. What it's just telling you is like this picture I don't really like too much, and a little bit deviating. Okay, every time you put the two materials together, there's a junction, and you're going to have a different voltage, meaning like different electric potential at this point, right? And that amount of voltage completely depends on the composition of these materials, okay? Which is composition of metal 1, composition of metal 2, of course, and they're always in a circuit, so equipped with some sort of energy, okay, that gives them the differences in the temperature. So that's why you're seeing hot and cold junction right there. But you always have a circuit around them in order for us to study the voltage, which is the electric potential difference. And that's from point to point. You've got the point if you put two things together. Okay? You always have a point. And that's what we study. For Thomson, the same thing. But the way that we put them together is a little bit different. So this time we're going to see the presence of the voltage, okay, and that voltage is now we're looking at the ends between the ends of the wire, okay, made from a single metal. So the wires are made of metal. So we have, if you have a wire, you have ends, and you have two ends, okay. So we've got voltage in between the two ends. You can get the voltage without energy source, okay. So if there is a temperature difference, so temperature difference is an indication, because that's just a measurement, indication of there is an energy, okay, in that circuit between the ends of that wire. So again, you've got a wire, and you have two ends of the wire, and we take a look at the voltage by changing the temperature, and we've got it, and that is Thomson effect. Here is, you've got two metals, you're going to put them together, make a junction out of it, and you have a voltage across it, okay. Again, you've got to have some sort of a temperature, okay, change, and of course it depends on the composition of the metal. Materials matter, okay. Materials matter because materials are composed of certain atomic structure, okay, and your properties depend on these structures, the internal structures. Okay, the amount of voltage again is determined by the wire, material, chemical uniformity of material, and the temperature difference. Here is composition and temperature. Here that voltage amount is determined by wire material, chemical uniformity, and temperature difference. Okay. All right. Thermocouple is just a device, look like that, and we have also quiet stuff. You can Google it. It's gonna come up a whole bunch of different devices right in there. Okay, you will see some pictures. So thermocouple is just a device, and this device uses the thermoelectric behavior of material. So thermoelectric behavior, you have two effects. Okay, I'll just show you in the previous slide. Your Peltier and your Thomson. And the total voltage, that total voltage depends on, again, temperature between the two junctions or 2 points, okay? And this thermoelectric behavior, and we call the Seebeck effect, okay? And that's just the name of the person who discovered that. So thermoelectric behavior, we've got it. We're always dealing with the voltage between 2 points or 2 junctions. And one of the devices that we develop by using the behavior is thermocouple. Yeah. So that voltage produced by the thermocouple device, you can measure it. And we're going to measure, since we're dealing with the voltage, we're going to use a voltmeter to measure. Okay. So voltage is again electric potential, and that electric potential comes from differences in temperature, so therefore we can also measure temperature after getting the voltage. Okay. So therefore, thermocouple device, we use it for precise thermometer, or we call it today precision thermometer. Very sophisticated, also expensive thermometer. Why? Because we can be able to get, okay, the measurement, which is your temperature, more accurately, okay, than using like whatever thermometer on site. Why? Because we are using the thermocouple device, okay, and then we get the voltage because they use a thermoelectric behavior discovering the voltage. So we can measure the voltage by using the voltmeter, and then we're gonna use that voltmeter measurement and then get the temperature. Okay, that's how the precise thermometer are built. Okay, the principle is a thermoelectric behavior where we discover voltage. Okay, voltage. This is just a picture. There's a circuit right there. Okay, so the reference junction of the thermocouple is placed at a known temperature. So that's your situation, okay, or condition that this thermocouple is set. So the electromotive force produced by the thermocouple is measured by your voltmeter, okay, and converted to a temperature reading. So right now, J1 that's just a junction 1, but that's a junction 2. The voltage is happening, okay, in between that 2. And we've got material A and we have material B. So we're dealing with the Peltier effect. Okay, we have a 2 junction. We have a differences in temperature. We can get this temperature by getting the voltage of these junctions. So I have another junction here, J3 and J4, okay? And then we're going to transfer or convert that voltage that we get from these junctions, and then we're going to get the temperature reading, okay? It will be a little bit difficult for you to see it right now, but you don't really need to know this, okay? Most of them are very automatic, and this is just going into their level. Our level is you're gonna get just a voltmeter and you're gonna deep, and then tape, and then tip, and then read, okay? That number or value, okay, coming up in your voltmeter. So it's pretty easy to do it at our system level, okay? So there's no need to worry about it. It's a pretty good device, thermocouple is. Okay, electrical properties. They're very important in every industry, because every industry we have gazillion of products, okay, made with all kinds of materials, and we use incredible amount of electric energy. So if power is down, everybody go crazy. You know, you need power, 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 power. So the properties, electrical properties are these ones: resistivity, conductivity, dielectric. This is just insulator. Semi conductivity. Okay, half. This is whole, and this is half. And super, that's above that. Okay, conductivity. So anyway, conductivity, resistivity, and the insulation. So that's what we're looking at for electrical property, not just the insulation, so dielectric. Okay, so you gotta understand these properties, because if you don't understand it, you can't design. Okay, simple as that. So they're very important for designing, manufacturing, and also quality control. And what we're doing, we're always dealing with electronic components and systems, okay? You can't run the electronic system or components, your computers, many different electric devices at your house if you do not understand these properties. Okay. All right. So the industries, we often use these properties. Okay, and they're like electrical power transmission, distribution, computer, your television components, and lasers. Okay. At home, there are a gazillion of products using electric power. Okay. Resistivity is pretty important. Your resistors, oh my gosh, incredibly powerful if you apply them in the computer circuits. So this is a measure how well the material resists the flow of the electricity. Electricity is nothing but the flow of electrons, electron flowing. And every time electron flow, we get something called current. Okay. And if they're flowing between 2 points, you always have a voltage. So resistance, voltage, that's something flowing. This is flowing in a line with different points, so therefore you've got voltage. And that resistance is completely, they're like inversely proportional to each other. Okay. So if you have like a big resistance to that flow won't go. Yeah. If you have a little resistance to that flow, it's gonna flow. Yeah. And the more it flows, the more voltage you've got in that circuit. Okay. So it just a measure of how well the material, okay, that material resists the flow of electricity, because some of them won't let the electron move inside. Okay. And some of the material will let them move inside pretty quickly. So every time an electron move inside of a material, and we call them conductor because they can move, so therefore they can conduct. So therefore we call those material conductor. You're going to be producing something called current. Okay, current was a physical thing of current, just electron ding dong, and moving. Okay, along. So how are they moving? They're moving through the structures. So one electron in the orbit is going to jump to another, and it's been filled by the other electrons. So where the extra electron come from? From your electric source. You usually put your plug right straight into the outlet, right? And all that energy comes from the energy producing the electric grid of your region. Okay, there's a flowing incredible amount, and you see the wires all over, right? In your city or town. We put them underground, we put them in the air with a little pole, and they're flowing anyway, yeah? So it's kind of like a domino effect, like ding, ding, ding. But then in domino, it doesn't move, but them, they move position, yeah? In different positions. So we call this relationship between the current, the voltage, and the resistance Ohm's law, because that guy found out about this. Okay, so the resistance of the material is there. It is pretty much constant, and of course, all your material is subjected to a particular size. We call the part size or component size, the material size, and the temperature in which they are staying. Okay, because we're always like in a temperature, meaning like if you think of the room temperature, that's the movement of the total of all the material in that room. Okay, you usually think like air. That's all you think about, but the air you and then all the non-living objects around you, they're all moving to some degree because we're all subjected to sunlight. Okay, so that's another energy source which is completely activating all the atoms that we have in our body, all the atoms in the non-living objects, and then all the atoms in the gas, which is your air. Okay, so if you think about the room temperature, we're talking about the average movement of all of that, the total. Yeah, and you dip your thermometer and then you take a look at it, and oh, they're all moving and they're hitting this little sensor at the thermometer, and the thermometer is indicating, oh, they're moving that much because the reflection of their movement is the movement inside of your thermometer instrument. Okay, and then we translate it to a particular unit, and that's not the absolute, that's just a relative unit right there. is showing a measurement indicating the amount of movement of all of us, okay, in that room, and we call that room temperature. So the resistance of material is constant based on your material, which is in a temperature, okay, at a temperature, and then the size of that material. So that's your resistivity, resisting the movement of the electron inside of that material. Then R is your resistance. So this is another relationship that we discovered. So that resistance you can change, okay, by changing the size of the conductor, because we come to know resistance depends on the material size. It depends on the temperature of that material, and that material is in. There are two temperatures. One is the temperature of the material itself, and the other one is the temperature of the environment the material is set. Okay, so the resistance we can change. Oh, and we change the size of this. What is going to happen to it? So you change and measure again, change, measure, change, measure, and we got, oh, okay, if you increase the size of this conductor, the resistance go down. Yeah, if you decrease the size of the area, the resistance is going to go up, right? So that's a cross-sectional area, and that's a length. So if you increase the length of that material, the resistance is going to go up. If you decrease, okay, the length of that material, the resistance is going to go down. Okay, so when you study, you can start drawing like that. I'm going to make the length of the conductor longer. Okay, so the resistance is going to go down. Sorry, go up. What am I saying? Okay, and then the area, okay, the cross-sectional area. So a little bit difficult to draw the cross-sectional area, so it is kind of like that. So I'm going to draw like this. So we're talking about this area, okay? So when this cross-sectional area is going up, your resistance is going to go down, yeah? So for length, it's going to go up, resistance will go up. For cross-sectional area, when it go up, okay, the resistance is going to go down. So when it go down, the resistance is going to go up, okay? So inversely proportional, and that's directly proportional. Everything under the fraction bar is going to be inversely proportional to something across the equation, okay? And that's just the role. I'm just showing you the resistivity of that material. So materials with high resistivity, we're going to use an insulator because electron cannot go through it easily. Okay, now this is your electron coming out from your power, okay, source. So I'm going to draw a little plug right there going into your circuit here. So materials with low resistivity, when you check this value is low, you know that, okay, we're going to use as electric contacts, because since the resistivity is low, the electron will flow, the current will flow, okay? All right, I'm going to erase my mess here. I got a little bit better for drawing. Okay, so another table here. Again, concentrate on the material and light on your unit and stuff. Not going to ask you any of the units. So resistivity, okay, so these are all pretty small because they're in a -8 exponent, okay, so very, very small. All the small and all the big, giants, okay, value we use exponents because it's easier to write that way. And then go up. Yeah, this is pretty big. 10 to the power 16, pretty big, yeah? Your quartz, fused, sulfur, rubber, glass, and go all the way down to silver. So meaning like silver conduct better. Why? Because resistivity is very, very low, okay? Very, very low. So therefore, conductivity is going up. Here is your temperature coefficient, which is your little alpha again, okay? So when you pay attention, so if they're all the same, we just concentrate that. So that's bigger, that's going down, yeah? So offer going bigger, and we have already understand how they are connected, okay, in the previous equations. So try to take some time to relate the value here is higher and going down. It's very important that you can see that trend and then link to the material, okay? Everything else is going to come easily. Try to look at the number, but don't confuse yourself. Here, this is the same thing, so therefore you can have 1.59, that's like 150, okay? So that's a little bit going up and down anyway, when you pay attention. But we can fuse this all together. You can rearrange it according to these number, okay? So that's actually going all the way up. And then this one will come later, 11, then 10, and then 3.5, 5.6, and then 3.5, 2.8, 2.4, 1.7, and 1.9. So you can rearrange them if you want to see the trend. Right now, I just like a jumble right there. Okay, conductivity continue. Again, we're measuring how well the material. Then we always have a material right there, you know, conduct the electricity. So this little thing right there is sigma, and that's the rho. The sigma conductivity is associated with particles, your electrons, your ions, okay, because they conduct, mean like they are moving through the material. Every time they move, we call the current. So existing inside the material, okay, it's associated with particle existing inside the material. So when they move, you have extra electrons and ions come from the source, energy source, and then they're gonna push, okay, and the original one is gonna push out, so you got the flow, yeah, through the orbits of your atoms that's going on. These phenomena going on in there. So your conductivity, and that's your rho. Higher concentration of these particles, they result in higher conductivity because you need them to move. If they don't move, you won't get any kind of conductivity. So the higher the concentration of the particles, the higher the conductivity. Yeah, pretty easy to understand. And lower the concentration of these particles is going to result lower conductivity. Yeah. Then we come into something called dielectric, which is non-conducting. Every time you think about dielectric, well, coming into the opposite of conduction, which is non-conducting material. So this is non-conducting material, and we're gonna just push, okay, right into the plates of the capacitor, because you want to make some cushion to adjust the level of conductivity, so we stuff material. So this property is used to select the insulating material, okay? Because we need insulation in many of our devices. Otherwise, they're gonna explode, okay, or burn, or we can't control the thermal energy. So capacitance is ability of a material. So another term, C, a big C, ability of a device, ability of a material, and that ability is to store the charges, okay, electric charges, your ions. So your capacitance is equal to epsilon naught, and then A divided by D. Some people call it epsilon zero, the same thing. That's just a permittivity. We're looking at, since it's a capacitor, we have two little plates, okay? And if you have no material, that's just a zero, because there's only vacant space, just a space in between the two plates. So if you put some material, then you have material in between the plates. Because the capacitor is just plates like that, okay? And we're talking about this little space right in there. If there's nothing in that space, okay, we call that the permittivity epsilon naught, because that's the permittivity of a vacant space, okay? So vacant space, VS. So where permittivity is an ability to store electric potential, okay? we're gonna write another equation. So K is your dielectric constant, and that's your relative permittivity. It is relative because we are comparing, okay, the material that we're gonna put in between the two plates, okay, with the vacuum. So if you have no material, that's a vacuum, and we call that just a regular permittivity. So here in the vacuum has a permittivity, meaning like vacuum can store electric potential that much, okay, this much. So K is a dielectric constant. Now we're looking at, K is a relative, so therefore we're looking at against the vacuum permittivity. So we're looking at the permittivity of a material. Now we're stuffing something in between the two plates, okay? So as soon as you stuff, you don't have vacuum. Okay, sorry, so I just have to come back here. I was just trying to erase that. So anyway, so you have two little plates, and then instead of this space, we're gonna put some material in it, okay? Now we're looking at the dielectric constant. It's just a fraction. So we're looking at the ability to store electric potential, okay, electric potential voltage. So that's over the permittivity ability to store the electric potential in a vacuum space. Okay, so it's just a little fraction that we're looking at, and we call that the dielectric constant. So relative permittivity is the ability of a dielectric material to store the electric potential, okay, in relation to vacuum space. So this little epsilon is a permittivity, okay, which is this guy right there, of dielectric material. I'm going to erase this so it's easier to print if you want to print. Alright, so that K, it's your dielectric constant, completely depends on the ability of the material to react and also orient itself to electric field applied. So capacitor, you always have some sort of electric field, okay, applied to that area. So when you do that, the material, okay, they have an ability, a particular ability. That is what material can do when it is subjected to something. In this case, the material is subjected by an electric field. So in that situation, the material reacts. So how did it react? It oriented itself, okay, to the electric field applied. And you're going to see when you measure the dielectric constant K, because it depends on, the ability to store, the material's ability to store the electric potential in that space. You're going to see it completely depends on the reaction of that material to the electric field, okay? So it depends on electric field, they're going to store electric potential, yeah? And that storing depends on their reaction to that field, electric field. So now we're going to take a look at the strength. So dielectric strength of an insulated material is nothing but the limiting electric field intensity, because we're subjected to the electric field. So the limiting electric field intensity above which electrical breakdown is going to happen, okay? It means that it can no longer store the charges. So you can store up to a point, and that point is above which the electrical breakdown happens. So in other words, it depends on the electric, okay? It depends on the electric field intensity. So you're gonna watch the electric field intensity, okay? And there's a point of electrical breakdown, and you don't wanna, okay? You don't want to go up to there, because if you go up to there, the electric material is not gonna store charges, okay, anymore. So we have to play with their strength, okay, and that strength is the limiting electric field intensity. But again, when we handle the dielectric from our system level, you don't have to worry about it because it's pretty easy. They're all devices, okay, and the devices always come with the limits, so you don't go over that. Yeah. Okay, so when you think about the insulating material, since we measure the insulating material by using the dielectric constant, we always have a dielectric strength, okay? And that's your little number, the K number. So, and then we're going to compare with the dielectric constant, okay, of air. And you will see they're always like, okay, greater than that of air. Because air is kind of more, we usually think air, even though it is a material, we think of it as a material less. Of course, bacon has no material. So anyways, that's how we think it's always greater because you have a solid material. So therefore, the electric, okay, dielectric constant is going to be greater than dielectric constant of air. So that strength varies, okay, it depends on, again, since the strength comes from the material reaction to an electric field, okay, how much they can store, it depends on the thickness of that material, moisture, okay, absorption of that material, the length of time, how long that material is staying there, because the wear and tear comes with it, and the frequency of applied voltage, okay, how many times are you applying that voltage difference. Okay, so moisture, contamination, elevated temperature, aging is wear and tear, and the mechanical stress, okay? They can definitely decrease your dielectric insulation power, okay, your strength. Alright, so another table. Tables are, don't freak out. It's just showing you the trend, it's just showing you the material, okay? So here we're gonna pay attention to the material. The same material most of the time, okay, your vacuum, your air vacuum has one. Air is a little bit more because there's stuff in the air, mostly gas, okay? So when you take a look at the dielectric constant, which is your K number, okay, this is dielectric constant, the same thing in a different unit, okay, volt per meter, and you're going to see that. K is not the same as that, okay, K is, this is voltage, okay, divided by the distance between the two plates of capacitor. So this one is your permittivity, okay, divided by your permittivity of the vacuum, okay, so relative value that you're seeing. So in common word, you will see how the number go up in certain place, right? So that means that this guy is 233. That's pretty big, meaning like it's really good insulator. Yeah, they can store a lot of charges. And then we have water and silicone oil. Okay, they're also good for insulation. Okay, I'm gonna stop for part one right here on the slide of 22, and then we will do part two. Okay, and in the next PowerPoint.